Every time you ask an AI chatbot a question, it feels almost invisible. You type a sentence. A few seconds later, an answer appears. No machine is visible. No server is in front of you. No cooling system is humming nearby. But behind that simple response is a real physical system: data centers, servers, electricity, cooling equipment, and surprisingly, water. So when people say AI uses water, what does that actually mean? Is AI literally consuming water as it works? Or is the real story about the infrastructure behind the technology? To understand it clearly, we need to go behind the screen and look at how modern AI actually runs. AI runs on powerful computers inside data centers. A data center is a building filled with servers designed to run all day, every day. When an AI model answers a question, generates an image, summarizes a document, or writes code, that work happens on servers. The more work those servers do, the more electricity they use. And when computers use electricity, they produce heat. That heat is where the water story begins. If too much heat builds up around servers, the equipment can slow down, shut off, or become damaged. So data centers are designed around one major challenge. How do you remove heat from thousands of powerful computers running at the same time? Some data centers use air cooling. Cool air is pushed through rows of server racks. The air absorbs heat from the machines, then moves away so the equipment stays within a safe temperature range. At data center scale, this becomes an engineered system of fans, air handlers, vents, sensors, and carefully controlled airflow. Many data centers use hot aisles and cold aisles. Cold air is delivered to the front of servers. The servers pull that air through the equipment. Hot air exits from the back. By organizing server racks this way, engineers keep hot air and cold air separated, which makes cooling more efficient. But air cooling has limits. AI hardware can generate a lot of heat in a small space. That is why some data centers use water as part of the cooling process. In many systems, water does not touch the computer chips directly. Instead, water moves through pipes, coils, or heat exchangers. It helps carry heat away from the building or from the cooling equipment. So the connection is not that AI itself needs water, it is that the machines running AI create heat, and water can help remove that heat. One common setup is chilled water cooling. In a chilled water system, water is cooled by mechanical equipment and circulated through the building. That chilled water helps cool the air going into server rooms. As the water absorbs heat, it warms up. Then it returns to the cooling system to be chilled again. This creates a loop that moves heat from one place to another. Another important method is evaporative cooling. When water evaporates, it carries heat away. That cooling effect can reduce the amount of electricity needed for mechanical cooling. But there is a trade-off. When water evaporates, it is consumed. It leaves the system as vapor. So, a data center using evaporative cooling may use less electricity for cooling, but more water. A data center using mostly mechanical cooling may use less water directly, but more electricity. That is why AI's water use is not one simple number. The impact depends on the cooling system, the climate, the local water supply, and the electricity source. A data center in a cool climate may need less cooling. A facility in a hot, dry area may face much more pressure. A data center using recycled or non-drinking water has a different impact than one using treated drinking water. So when people ask how much water AI uses, the better question is, where is the data center, how is it cooled, and what kind of water is being used? There are also two ways AI can be connected to water use: direct water use and indirect water use. Direct water use is water used at the data center itself. That can include cooling towers, evaporative cooling systems, humidification, or other facility needs. Indirect water use comes from the electricity that powers the data center. Some power plants use water for cooling, so even if a data center uses very little water on site, the electricity it consumes may still be connected to water use somewhere else. This is why the full picture includes both the building and the power grid. Now let's follow one AI request from start to finish. You type a prompt into an AI tool. That request travels over the internet to a data center. Servers process it. The chips inside those servers use electricity. As they work, they produce heat. Cooling systems remove that heat. so the equipment can keep running safely. If the facility uses evaporative cooling, some water may be consumed. If the electricity comes from a power source that uses water for cooling, there may be additional water use connected to the energy supply. Then the response travels back to your device. From your perspective, it felt instant. Behind the scenes, it involved networks, servers, electricity, cooling, and water-related infrastructure. That is the physical side of AI. One reason this topic matters is scale. A single AI request may seem small, but modern AI systems are used by millions of people. They answer questions, generate images, summarize documents, support search tools, assist with coding, and power business software. At that scale, computing demand adds up. Training large AI models can also require intense computing over long periods of time. And after a model is trained, using it still requires computing power every time someone sends a request. Both training and everyday use require computing. Both produce heat. Both depend on cooling. This does not mean every AI prompt has the same water footprint. It means AI's impact depends on the infrastructure behind it. To measure efficiency, data center operators use metrics like PUE and WUE. PUE, or power usage effectiveness, looks at how efficiently a data center uses electricity. WUE, or water usage effectiveness, looks at how much water a data center uses compared with the energy used by its computing equipment. These metrics help companies track energy and water efficiency, but they still need context. A data center could use very little water on site but rely on electricity from a water-intensive power source. Another could use more water directly but rely on recycled water instead of drinking water. One facility may be in a region with reliable water supplies. Another may be in a drought-prone area. So water use is not just about the amount. It is also about location, timing, and source. Engineers are working on ways to reduce the impact. One approach is making chips more efficient. If chips can do more computing with less electricity, they create less heat. Less heat means less cooling is needed. Another approach is improving data center design. Better airflow, smarter controls, improved server layouts, and more efficient cooling equipment can reduce wasted energy and water. Liquid cooling is also becoming more important. Instead of relying only on air, liquid cooling can move heat away from chips more directly. Some systems are closed-loop, meaning the same fluid circulates repeatedly rather than being constantly consumed. Other facilities use recycled water, rainwater, or non-potable water for cooling. Some data centers are also built in cooler climates, where outside temperatures reduce cooling demand. All of these choices shape the footprint of AI, but every solution has trade-offs. A system that saves water may use more energy. A system that saves energy may use more water. A design that works well in one climate may not make sense somewhere else. That is why the issue is not as simple as saying AI is good or bad for water. The real question is how responsibly the infrastructure is designed and operated. The most honest explanation is this: AI does not literally drink water, but the data centers that run AI need cooling. Some cooling systems use water directly. The electricity powering those data centers can also be connected to water use. And as AI grows, those design choices become more important. So how does AI really use water? Computation uses electricity. Electricity creates heat. Heat requires cooling. Cooling may use water. Electricity generation may use water too. And the final impact depends on the system behind the screen. The next time you ask an AI tool a question, remember that the answer did not come from nowhere. It came from servers, data centers, power systems, cooling equipment, and engineering decisions working together in the background. That is the hidden infrastructure of AI. And like many systems we rely on every day, the better it works, the easier it is to forget it exists. If you enjoyed this video, make sure to like and subscribe to Hidden Infrastructure of the World. Also, comment down below what hidden infrastructure you want to see next. See you in the next video.